So in yesterday's lecture, we looked at the perceptron learning algorithm, and one of the shortcomings of the perceptron learning algorithm is that it can basically be used with linear separable problems only, so it can only be used to train a neural network that has a single layer. The backpropagation learning algorithm can be used in cases where you have multiple layers. So for example, if you have a multi-layer perceptron neural network, you can train it using the backpropagation learning algorithm. Look at today. So the main algorithm, or the first algorithm that was introduced when training multi-layer neural networks, is the backpropagation learning algorithm. It's also been referred to as the generalized delta rule, and it falls into the category of gradient descent algorithms, where the gradient of a function can be used to see how the function would increase or decrease. There's the stochastic gradient learning algorithm as well, which also falls into this category and is used to train neural networks. So if we look at the backpropagation learning algorithm, as its name suggests, basically what happens is you work in the way you normally do with your other algorithms, like the perceptron learning algorithm, where you train from your input layer going through to your output layer. The difference here is once you get to the output layer, the error in the output or activation from the neural network is compared to the target values in the instances in the training set, and that error is then propagated back through the neural network up into the layer just before the input layer. Based on this error, the hidden layers and the output layers, the weights that were calculated, the biases that were calculated, those values are then updated accordingly. So those are the three processes that make up the backprop algorithm. In the course, we are going to look at one variation of the backprop algorithm, but you'll see there are a number of different variations. The main way in which they seem to differ is the mechanism that is used to update the weights. So you'll see different variations where different mechanisms are used for this. If we look at the architecture compared to the architectures that we've looked at previously, so the main difference here is you have hidden layers. So you have an input layer and you have an output layer like you did with the perceptron neural network architecture. But in between both those layers, you can have one or more hidden layers. You have to have at least one layer, otherwise it's again reduced to a single layer neural network. Like the perceptron neural network architecture, the backprop or the multi-layer neural network that the backprop is applied to also has a bias. The activation functions that are used are quite different from those used with the perceptron learning algorithm, and the main reason being is that these functions have to be differentiable. So when that error is actually calculated, differentiation is performed on the activation function in order to calculate that error. So your functions have to be differentiable. At an example of the architecture that you can apply the backprop learning algorithm to. So if you look at the example neural network, there are three layers. There's one input layer. That input layer has three inputs and an input of 1 for the bias. Note the notation that we're using for the bias is different from yesterday. Basically, all the biases start with an index of 0 to indicate a bias, and then it maps to the next layer, and the following index is that of the node in the next layer. So for example, V01 maps from the input layer to the hidden layer, 0 indicating the bias and 1 indicating the first node in the hidden layer. The hidden layer has 2 nodes and 1 bias. Now the number of nodes to actually include in your input layer and the number of, in the hidden layer, and the number of hidden layers that you want to include in your architecture, this differs from one application to the next, and this is one of the design decisions that are made when you're designing a neural network. The final layer is your output layer, and the output layer has 2 outputs. And again, there's a mapping from the bias and the hidden layers to the output layers, and the weights in that layer we've labeled with W's, and the weights from the input layer to the hidden layer we've labeled with V's. So if we look at the backprop learning algorithm, It's made up, like I said, of the three processes we spoke about just now. But the initial step, like with the perceptron learning algorithm, is you've got to initiate or initialize the weights and biases. These are initialized again to small values, random values of 0. The one difference between this algorithm and the perceptron learning algorithm is that the activation functions used with this algorithm are very, very sensitive to the weights and bias values. So those values need to be chosen very carefully. And typical ranges that have been used are ranges like, for example, minus 0.5 to 0.5 or minus 1 to 1. So here when we speak about convergence, the convergence is slightly different from what we spoke about yesterday. We're speaking about convergence of the error. Yesterday when we looked at convergence, we spoke about convergence in terms of the weights and the bias, no changes to the weights and bias. So here your stopping condition could be when the algorithm detects errors, and those errors, there's no change from one epoch to the next in the error. Alternatively, the error starts increasing. So in that case, you would actually terminate your algorithm. The three processes that make up the algorithm are, again, the feed-forward learning. That's basically the training process which we spoke about in the perceptron learning algorithm yesterday. So it's determining the weights and the bias. And remember, we calculate a value of n and apply the activation function to that. The backpropagation of the error. So once that learning process happens and the neural network produces output, those activations that the neural network produces are then compared to the target values in the training set, and the error between the target values and those values are then propagated back. So based on the error values propagated back, the weights and the biases are then updated. I shouldn't have actually hit this activation functions. It's what the activation functions are applied to. So we spoke about the activation functions just now, and those are some type of sigmoid function. But if you remember from the perceptron learning algorithm, those functions are applied to a value n, and we're going to look at how n is calculated basically in the same way that it was done for the perceptron learning algorithm, but here we have different layers, so we have to label it differently to differentiate. So remember, J looks at the number of units. It's basically the number of units in your hidden layer. So your N1J, N1 is just indicating that the function is N1 as opposed to just N, because we're going to have a second function again, which will be used for the output layer. J is referring to the jth unit in your hidden layer. And again, we're taking the sum of the bias, which here is V0J, and the weighted sum of the inputs. So your inputs are going from 1 to n, and P represents your inputs, and the VLJ now represents your weight going through to from the input layer that represents your L to the hidden layer that's indexed by your J. So if we look at the output layer's in function, which an activation function will be applied to, is differentiated from the one from the hidden layer by indexing it with a 2 instead of a 1. Also, your nodes at the output layer, these go from 1 to m. So m is representing your nodes at the output layer. So again, you've got the bias, and the bias in this case is W0M, and that's added to the weighted sum of, now we don't have inputs, but we have the output from the previous layer, and the previous layer being the hidden layer. And that's represented by F, which is representing your activation function applied to the N1 function from the hidden layer. And that is now your weighted sum of inputs, but the inputs are from your hidden layer rather than from the input layer. So that's basically the first part of the algorithm complete. Is looking at performing your feed-forward learning. So for each node in your hidden layer, you're going to calculate the N1 that we just looked at, and then you're going to apply F, which is the activation function. And then you continue and you do the same thing for the next layer. So if you had 2 hidden layers, you'll do this for each hidden layer. And here you then go on from the hidden layer, you go on to the output layer, and then you'd calculate N2 for each output layer, and then you'd calculate the activation function. So that's basically the whole process involved in performing your training for the feed-forward learning. So the next step is to now propagate these errors back once you've got to the output layer and you've worked out the difference between your target output values in the training instances and the activations of neural network. So before we look at the algorithm itself, we're just going to look at the different equations that you actually have to calculate to do this. So I'm going to call these the backpropagation of error equations. The first term that we could calculate, and we do this for both, we start doing it from the output layer, and then we do this for each hidden layer as well. So for each hidden layer and for the output layers, we have an error information term. You'll see we have a weight correction term and we have a bias correction term. So again, you remember we're at the output layer now, and the number of nodes we have is m, and we're indexing this by k. So k is going from 1 to m. And basically what we're doing is we're taking the difference between the target value specified in the training instance, so this is tk, and the activation of the neural network, which is fn2k, and we're multiplying that by the derivative of fn2k. We then use this value to calculate the weight error term. So we're still at the output layer, but you must know we're now actually going to map back to the hidden layer from the output layer. So J represents our nodes, the number of nodes at our hidden layer, and this is indexed by I. So basically the change in your weight error term is going to be alpha. Now alpha is a learning rate. We also spoke about alpha yesterday with the perceptron learning algorithm, and alpha can be used to control the rate of learning. And different values are used. Often fractions are used for this. You could also use a value of 1. Again, the best value to use is problem dependent. That's multiplied by the error information term, and then the activation of the neural network at the hidden layers, then multiplied with that to work out the weight error term, or the delta in that case. In the same way, you've got your bias error term worked out in a similar way. The only difference is that we don't include the activation here. We don't multiply by the activation, so it's just the learning rate times the error information term. So remember now, for each layer, we're going to calculate these 3 measures when we're calculating the error. So if you had n hidden layers, you're going to calculate this n time from the hidden layer, but there must be some way of getting this information from one layer to the next when you're propagating the error back. Done is by using the sum of delta inputs. So in this case, the sum of delta inputs are actually being calculated from the output layer to the hidden layer. If you had another hidden layer, so we're looking at the algorithm for just one hidden layer here. If you had another hidden layer, then the same would have to be calculated from one hidden layer to the next hidden layer. So the equation for this, basically we're taking the sum of our delta k values and we're multiplying it by the weight. And so remember again, m refers to the number of nodes in the output layer, and our I indexes the nodes in the hidden layer, and that goes from 1 to j. So as we did for the output layer, we then calculate the 3 error terms for the hidden layer, and that's the error information term, the weight correction term, and the bias correction term. So if we look at these equations, they're very similar to the previous ones. So now we use the delta ni value because we had a hidden layer and we no longer have a difference between the target value and the activation. The delta ni value, which we calculated as the sum of delta terms in the previous slide, that value is now used instead of that difference. And again, we're taking the derivative of the activation function at the hidden layer node. The weight error term, again, is worked out in the same way that the weight error term was worked out for the output layer. We'll be using our alpha learning rate. We use the same alpha learning rate, our delta I, and the difference this time is now we're using an input value from the input layer. Similarly with our bias, as in the previous case, we didn't use the activation when we calculated the bias, so here we don't use the input value as well. We're basically looking at the alpha times the delta I value. So if we look at the algorithm for propagating the error back through the neural network, it's basically using each of these equations. So if you look at line 1, that involves calculating your error information term for the output layer. And then similarly for your next layer going forward, you're going to do the same 3 steps. So we've got calculating your error information term, calculating your weight correction term, calculating your bias correction term. In between them, remember we worked out, and that's indicated in step 4, we worked out the sum of the delta inputs for each node, and that was to actually allow information to be transferred from the output layer to the hidden layer. So we did this for each node in the hidden layer. And then again, we performed the same 3 steps for the hidden layer. So if you had another hidden layer, again, you'd work out the sum of delta inputs between the layers, and then you'd work out the 3 values again for that hidden layer. So the error information term, the weight error term, and the bias error term. So this basically is what gets done to propagate the error back through the neural network. Once that error is propagated back, we can then use that error to work out the weight and the biases. So if we look at the weights and the biases, we need to use an equation again to update these based on the error. So the equation used at the output layer is basically the old weight value or the old bias value plus this change or this error function that you've actually moved back or you've propagated back. Similarly for the hidden layer, the new weight is the old weight and this error value that's been propagated back. Again, just a reminder, we've got J hidden layers and we're starting I from 0 to J. So this is referring to what happens at the hidden layer. Here the zeros there to look at the update for the bias. Your output layer has M nodes at the output layer and K is indexing that. At your input layer, you have N inputs, but the 0 there is to again deal with the bias, and your index variables I indexing that. And then lastly, in your hidden layer, you've got I going to 1 through to J, depending on whether you're looking at the output layer or the hidden layer when you're actually doing the calculation. So that's when you're dealing with the weight, it's going to start at 1. When you're dealing with the bias as well, it's going to start at 0. So the last part of the algorithm is to update the weights and bias using these equations. So we update the weights and bias for the biases for the output layer, and we update the weights and biases for the hidden layer. So that's basically the perceptron learning algorithm. Now, once these algorithms have performed training and we know the weights and biases, what do we do with them? So if you look at supervised learning, we know we train, and then once we train, the idea is to test to make sure that our classifier or our function emulator works on unseen data. And so if you're using the perceptron learning algorithm, or if you're using the backpropagation learning algorithm, you're going to train, and then after you train, you're going to test. So as we spoke about yesterday, you're going to need a test set, and you're essentially applying 2 parts of this algorithm. You're applying the equation for that takes the weighted sums of the inputs and the bias, and in addition to that, you are going to apply the activation function. So you'll take that same weighted sum, and now the inputs will be a vector in your training set of inputs. You're then going to apply the activation function to that, and that activation function will then produce your output, and what your output will be given that training input for the unseen data. So that brings us to the end of the backprop algorithm. Tomorrow's TAT will be on the multi-layer perceptron algorithm using the backprop algorithm, and will be on the perceptron learning algorithm and the perceptron architecture. Next week, we'll look at a recurrent neural network. So we'll look at the Hopfield neural network in Tuesday's lecture, and then we'll start looking at deep learning and convolutional neural networks in Wednesday's lecture.